So we all know the equations of motion, or suvat equations, but we do need to know how to derive them. So let's start by looking at this diagram where you have a velocity time graph, and the initial velocity of this object is u meters per second and the final is v. And in time t, it reaches that final velocity. Okay, so a couple of things we already know is that the gradient of a vt graph, which represents acceleration, it could be written as the change in the y-axis, okay, change in y-axis over change in x-axis. So the gradient is a, okay, and the change in the speed, or velocity, over change in time could be written as v minus u over time t, okay, and so a is equal to v minus u over t, which we have seen in GCSEs as well, but if we just rewrite it to make v the subject, we'll end up getting v as equal to a times t plus u, okay, so u plus at. So this is our first equation of motion, and from here now we can check out the rest of them as well. So the second equation that comes to my mind is the equation for the displacement, s equals ut plus half at squared. Okay, so let's go ahead and prove that. Okay, that's one of the very important equations that we use in projectile motion as well, and it's given to us in the formula booklet, so we don't have to worry about remembering them, but it's still worth it. If we talk about the displacement, or in this particular case, the area under the graph, there are two sections. There's one area which is this rectangular area, okay, and that is equal to u times phi t. And then there is an area of this triangle which is given to you as half height times base. Okay, so height is obviously v minus u, and the time is the base. So the total displacement, or the total area, one and the same thing. So we can say that s is equal to ut plus half v minus u times t. Okay, now what we can do is simply replace, so we already got the first term ut, okay, but we need to get rid of the v minus u, okay, from here, and we know that from the first equation, v minus u can be written as a times t. Okay, so I'm going to put that into here. So s is equal to, therefore, ut plus half a t, okay, times phi t, so t squared. Okay, so really simple proof, and in 2 steps you can actually just do it. Now, the next proof that we have, the next equation that we have is s is equal to half u plus v times t. Now, we don't often use this equation, but it's still very, very useful. It's almost like a hidden gem. Okay, it's very useful when you don't have the acceleration, in the question. So, for this equation, we just need to consider the area of a trapezium, okay, without really worrying about the acceleration. So the trapezium can be probably seen, if I just highlight it, you can see that this bit is like a, okay, so the area of a trapezium is half a plus b times pi height, okay, and this is b, okay, so that's v, in other words, and the height is t, okay, so it's like a sideways trapezium, okay. And so if I just use the area or displacement as s equals the area of a trapezium, okay, it is half times u plus v, okay, a plus b, so u plus v, times phi, the height, which is t. So it's really as simple as that. Now the last equation is, again, very important. Let's just zoom out slightly. And the last equation is v squared, let's go for that, alright, so v squared is equal to u squared plus 2as. So let's prove that. So we're going to need the first equation, which is right here, and the third equation, which is right here, to prove this. So let's first of all, so we can clearly see that there is no t in our final equation. So we therefore must make t the subject from the first equation and insert it into the third equation. Alright, so let's make t the subject from the first equation. So from 1, I'm going to say that t is equal to v minus u over a. Okay, and I am going to substitute that into my third equation. Okay, so into number 3. So that becomes s equals half times u plus v times by t, which is v minus u over a. Okay, now let's simplify this as much as possible. So I'm going to multiply both the sides by 2 and a. Alright, so 2as. Okay, and then I'm going to have u plus v and v minus u. And if I expand the brackets, I'm going to end up with difference of two squares over here, right? Which is v squared minus u squared. Okay, and there you have it. You have v squared equals, if you add u squared to both sides, you are going to end up with your final equation. So although these derivations haven't been asked yet directly in the exam, because it is in the textbook and you are meant to know them, they can be asked, in the exam. So make sure you are able to derive these suvat equations. Pressure in fluids. Now this is an important proof, which is to prove that pressure equals rho gh. Rho is the fluid density, g is the gravitational field strength, and h is the height of the column or the object that is submerged. So over here I've got a cylinder of height h, which is submerged fully, and it has a cross-sectional area of a. Now pressure is equal to, in general, force divided by the cross-sectional area F over a. And we also know that the force over here is equal to the weight of the object, weight of the cylinder, divided by the cross-sectional area A. So let's understand what that weight is, okay, in terms of not just mass times gravity, but we have to manipulate it slightly, ever so slightly. So we know that weight W is equal to mg, okay, and where m is the mass of the cylinder. And we can say that the mass of the cylinder is equal to the density times by volume, okay, density times by volume, and that's just times by g, okay. And if the volume v of the column is a times h, which is the cross-sectional area times the height, we can just rewrite v as that, and that's gonna end up looking something like this. Now if we put this form into our pressure equation, then pressure is equal to rho ahg over a, okay, where a's cancel out and it gives you rho hg, and that's your pressure in fluids. And so bear in mind that pressure is independent of the cross-sectional area, and it is clearly dependent on the density of the fluid as well as the height of or the depth at which the object is. So as the depth increases, the pressure will also increase. And since density is proportional as well, the denser liquids will therefore exert more pressure. Let's prove the resistors in series and parallel formulae. So let's start with series, and you may have seen this before. It's really simple. There are two things you need to know. Number 1, Ohm's law, and number 2, the fact that in a series circuit, current remains the same, whereas the voltage is shared. Okay, so if we base that, let's start with V equals I times R, where V is the total voltage, I is the total current, and R is the total resistance. So if I just wanted to write down V, the total voltage, okay, as I times R, okay, the total voltage can also be written as V1 plus V2, okay, because the total voltage adds up. And so I times R equals V1, which is essentially I1 times R1 plus I2 times R2. However, I1 and I2 are the same. So that means that I times R equals I can just factorize that out, and they can just cancel out. So this is what gives you R equals R1 plus R2. Now similarly, if you're talking about a parallel circuit, then the voltage remains the same. Okay, so over here V is equal to V1 is equal to V2, but the current adds up. So I is equal to I1 plus I2. So for that, you can just use the Ohm's law again, where it's V over R. Okay, I1 is V1 over R1 plus V2 over R2. And because V1 and V2 is the same as V, it cancels out. And it just gives me 1 over R1 plus 1 over R2 in brackets. And there you have it. 1 over R is equal to 1 over R1 plus 1 over R2. Okay, so this was really simple, and you may have learned this. You may not even have to worry too much about it, as it doesn't tend to come up as much in the exam as other derivations, but it's still worth knowing these proofs. So this is one of my favorite proofs, and the concept itself is pretty fascinating. The total internal reflection just simply means that if you had a ray of light going from one medium into another, in particular a more dense medium into a less dense medium, the light will be reflected into the first medium, the more dense medium. Okay, what I mean by that is that, say you have a glass air boundary, and we know that glass is more dense. Okay, so I'm going to call it N1, the refractive index of medium 1, and N2 as the refractive index of medium 2. And we know that N1 over here is greater than N2 as it's denser. Now, if a ray of light was to go from the first medium into the second medium, so if it was something along the lines of here, now, at some point, if the angle is just right, the light will be reflected into the first medium. Okay, now, what is that angle that we're talking about when the angle is just right for it to reflect all backwards into the first medium? Well, we're going to find out. So let's just get rid of this and understand this from the start. Okay, so say you have a ray of light going from glass. Okay, it's making an angle I, which is the angle of incidence. Now, as it goes out into air, it would bend away from the normal. Why? Because it's speeding up. And this angle is angle of refraction. Okay, this is angle of refraction here. Not to confuse it with the angle of reflection, because they are denoted by the same letters. So I'm going to just put it down here. Okay, now that's the first case, right? Nothing unusual is happening here. However, if we were to increase this angle of incidence slightly, so that the angle of refraction became 90 degrees, okay, to the boundary, to the normal. So this right here, okay, that is crucial. This angle of incidence, for which angle of refraction becomes 90, is called the critical angle. I'm going to call it C, okay, capital C. So I'm going to write this down. So C is the critical angle, and it is the angle of incidence for which the angle of refraction is 90 degrees. And beyond this now is 90 degrees. Beyond this, if we were to increase the angle of incidence more than this, so I is greater than C, let's draw that out, we would notice that all the rays are going to be reflected into the first medium, that is the glass. Alright, I may not have drawn it perfectly, but I hope it gives you some idea. So this angle over here, the blue angle, alright, I'm just going to put it down here. This angle is angle of incidence, which is greater than the critical angle. And this angle over here is the angle of reflection now, okay? Reflection is happening. So if we now apply this, so you guys may have heard of Snell's law, or the law of refraction, which simply states that angle N1 sine I, or sine theta 1, is equal to N2 sine theta 2. Now I can make it more clear and just use I and R, where angle R is the angle of refraction. So if I now apply this to this particular situation of 90 degrees refraction angle, I can say that N1 sine C is equal to N2. Okay, now N2 in this case, and in most cases, especially in your textbook, in the OCR syllabus, N2 is going to be air. Okay, so the second medium is air, which has a refractive index of 1. Okay, so we can replace N2 with 1, and sine r is sine 90. And sine 90 is 1, okay? So that side becomes 1. And therefore, sine c becomes 1 over n1, or just n in general, where n represents the refractive index of medium 1, okay? Medium 1. And obviously that was that of air in particular, okay? Now, if air wasn't used as a second medium, then it would be n1 sine c equals n2 sine 90, which is just 1, and therefore n2 over n1 is going to be equal to sine c. So this is very generic, whereas this is in particular for the second medium being air. I hope this helps. So over here we have got a Young Double Slit experiment set up. We have two slits, S1 and S2, and they are 8 meters apart from the centers. And we have 2 points, X and Y, where the 2 bright fringes are being formed. And the distance between the two is X. And finally, the distance between the slits and the screen is D meters. So D is much greater than A for this particular model to work. And so if we considered the path difference, which is basically this S2P, okay, that is going to be equal to just a lambda, one whole multiple of lambda. Okay, why? Because we have bright fringes concerned. And for bright fringes, we always take whole multiples of lambda rather than for dark fringes where we consider n plus half lambda. Okay, so that's going to be lambda. Now, if we took 2 different triangles, so I'm going to take the first triangle as S1, S2P, all right? In that triangle, I know that sine theta 1 is going to be equal to lambda over A. And that's because it's opposite over hypotenuse, all right? So lambda over A. Now, we also know that the triangle, which is marked with X, Y, and let's call this A, okay? I'm running out of letters. So X, Y, and A. In that triangle, we can use tan theta 2, which is equal to opposite over adjacent, so X over D. Now, with these 2 angles, or triangles, we can equate these 2 functions because theta 1 or sine theta 1 is approximately equal to tan theta 2. And the reason for that is that theta or angles are very small, okay? And we can therefore equate lambda over A to X over D. And we will get the required relationship as lambda equals AX over D. And this is a formula given to you in the exam. However, it's still worth knowing the proof just in case it comes up in the exam as it is in the textbook. Now, the relationship between De-Broglie's wavelength and kinetic energy has not been asked to prove as of yet. However, you do need to know what it is, at least, and its lambda, which is the De-Broglie's wavelength, is inversely proportional to the square root of the kinetic energy. Okay, so we're going to prove this real quick. And let's start with De-Broglie's wavelength being h over mv, and where h is the Planck constant, and the kinetic energy is half mv squared. So if I want to get rid of this m times v from the bottom, I need to introduce an ek. So let's manipulate this equation and see what we can get. So let's multiply both the sides by 2. So that would give me mv squared. And I'm going to multiply both the sides by m as well, because I can then get an m squared v squared, which I can simply square root. So I would end up getting a direct expression, which I can substitute into that equation. So I would get lambda equals h over square root of 2ek times by m, where h and m being the mass of the electron, is constant. So we can safely say that the lambda is inversely proportional to the square root of the kinetic energy. So if you decreased the kinetic energy by a factor of 2, the wavelength will increase by a factor of square root of 2. Okay, so worth knowing this one, as it has been asked a few times in multiple choice questions.